Hello friends, welcome back to another video. So remember last time we showed that if we take a Lagrangian of the coordinates and the velocities to be this quantity g mu nu, g mu nu is the metric, at q times q dot mu, q dot mu. I don't remember if we had a 1/2 or not, but I guess it doesn't matter. So if we take that to be the quantity and we plug that Lagrangian into the Euler-Lagrange equations, we saw that we get the geodesic equations. And I showed you on an example when g mu nu was just the Minkowski metric, I think. Or maybe I did it even just for the regular Euclidean metric, Riemannian, whatever. Okay, so now I want to do it on a cylinder. Okay, so we're going to be looking for geodesics on a cylinder. This is just space, no space-time. We're only going to be looking at, so okay, let's do that like that. Oh, that's really pretty. So we have x, y, and z, right? And so inside the cylinder, we have r, which we're going to keep fixed. Z is just normal, z. And then we have an angle, best to measure like that. That's theta. I'm sorry, that's a little too small, but I mean, you know what a cylinder is. Okay. And so from here, I can write that x is r cosine theta, y is r sine theta, just your standard polar coordinates. Nothing too extravagant so far. And so, the regular, if we had L, X, Y, Z, right? The regular metric would be g is ds squared, it's dx squared plus dz squared, dy squared plus dz squared. Okay. Here, right, z is z. So this is going to give us that dx is dr cos theta minus sine theta r d theta. So I'm just differentiating, right? I'm doing partial differentiation here. So dx is del x by del r dr plus del x del theta d theta. That's what I'm doing, and I'll do that for all three, right? So dy is dr sine theta plus r cos theta d theta, and dz just stays dz. Okay, so we plug that into G, but not before I impose. So impose r equals constant, so dr equals 0. So what does this do? It fixes the position of the particle to be on the cylinder. So this particle is living on the cylinder. It's like, here I have a cylinder right here. So imagine that an ant was moving across this jar. And so obviously the cylinder is the only place the ant can move on. It's confined. So yeah. Okay, I can just move down. Oh, that's pretty nice. Didn't know that. Okay. Okay. So we fixed R. Sorry, my computer's making noises. Okay, cool. So we fixed R, and that reduces our dimensionality by 1. You see, and now here it seems like we have 3 metric components, but in reality we'll only have 2. I mean two non-zero ones, right? So if I find dr squared, sorry, not dr squared, dx squared, it's just this term squared, just this term squared for dy, and just that, right? Because dr is 0. Okay. So we'll just end up having dz squared plus r squared d theta squared, because sine squared plus cosine squared is 1. I think I have a video on that. So dz squared plus r squared d theta squared, that's our g. So g is, if we write it in matrix form, although that's, g is not a matrix, but okay. So if we write it in matrix form, I'll be writing like, I guess this will be z and theta. So it will be 1, r squared, 0, 0, okay? And then our Lagrangian of z dot, theta dot, will just be g mu nu of z theta. But as you can see, it doesn't actually depend on z and theta, which is pretty nice. None of the components, they only depend on r, which is fixed, constant. And then here we have q dot mu, and so q1 is z, and q2 is theta, right? So I'll be plugging in z dot and theta dot. Yeah, and so obviously, maybe I'll write it down. G11 is 1, and G22 is r squared, and let's just not forget that this is constant. Okay, cool, fixed. Awesome. So now, I mean, you know the Euler-Lagrange equations. This is first grade stuff. We see that this is equal to 0 because there's no z dependence in g mu nu. And this one too is 0. So both z and theta are cyclic, we say. They don't appear in the Lagrangian explicitly. Okay. It's just a fancy term. Cool, so they're cyclic. So what does that mean? It means obviously that d by dt del L by del Z dot is 0, and d by dt del L by del theta dot is 0, okay, because that's on the other side of the equality in the Euler-Lagrange equations. And this means that g mu nu, not g mu nu, let's be careful here, okay? So let me just write it generally. Since both of them are equal to 0, I'm allowed to write it like this. So del L by del q dot mu, that's equal to d by dt. So now I just differentiate. I'm gonna get 2 of them because remember, I'm not differentiating with a particular index, but to all of them. So I'll get 2 g mu nu z theta, or I'll just write q dot mu. So this is over mu, so the mu index is kept, the mu is summed over. And okay, and so yeah, we're obviously only left with the diagonal part. So this means that I'm gonna write it as this thing equals constant, because if the time derivative is 0, then the thing inside is constant, and I'll drop the 2 because this is equal to 0. I'll drop the 2, divide by 2. So I have that G11 z dot plus G12 theta dot is constant. But of course, G12 is 0. And I have the G21 z dot plus G22 theta dot is constant. But of course, G21 is 0. Okay. So we can plug everything in. G11 is 1, so we have z dot. Maybe I'll call that p over m is constant, where p I want to represent momentum by. Obviously this could be a light particle, a photon. So then dividing by mass is a little bit of an oopsie, but I mean, I still want to write it like this. And theta dot is equal to, so we have r squared theta dot. Okay, that's angular momentum, right? Let's say that mass is equal to 1, so I'll just write p for z dot, and then this can be L. Note that this is not the L of the Lagrangian. Maybe I'll write it as little l. It's also constant. So basically this is like conservation of momentum, conservation of angular momentum, which we really should expect as physicists if we're looking for geodesics. Nothing is accelerating the particle, so everything has to be conserved. We can also check that the energy is conserved. So yeah, let's do that. That sounds fun. So basically, what does this mean? This means that z dot increases linearly with time. So our particle, let me just maybe make it really look like a surface. Our particle, it's going to be red. It wants to move upwards or downwards depending on the sign of p, of the initial momentum. And it wants to move sideways in theta depending on the initial angular velocity. So maybe I'll do that in blue. It wants to move like that. And so the actual trajectory, okay, I'll do it green. The actual trajectory looks something like that. Okay, now this should be infinite, so something like this, right? And then it goes the other side there, and you know, maybe it'll do something like, let's say there's one parallel downwards, so it'll go like that, and then again, right? So this is the same one. Let's call this 1 and call this 2. Yeah. Obviously everything depends on the initial velocity and initial angular momentum. I mean, velocity is encoded into momentum, right? So yeah. So yeah, that's pretty nice. So in particular, if the initial velocity is 0, then the angular velocity is the one that dominates, and so the particle will just go around. I mean, it basically tells you what you already know, right? So if I were to take this cylinder and there were no gravity, and I just flicked an ant like that, it would just keep going. No losses to friction, of course, because we don't know what friction is. Just going like that. If I flick the ant like that, and well, a third dimension didn't exist, then the ant would just go around. There you go. Or if there were some forces constraining the ant to stay. I mean, you can think of models. Cool. Okay, let's just check out the energy real quick. So the energy associated to this, I mean, we can see that this is just momentum, right? But the proper formula is, I believe, partial Lagrangian with respect to q dot times q dot minus the Lagrangian. Now, of course, this is just 2 times the Lagrangian, the whole thing together, right? We already calculated that. So I'm not pulling a fast one over you, see? So it's just 2 times the Lagrangian, so it's equal to the Lagrangian. And if we take d by dt of the energy, well, let's see what we get. I'm not actually sure. Was this wasn't part of, okay, so we'll have g mu nu dot so we have, let's write it all, G mu nu, Q dot mu, Q dot mu. So this will be, I take the partial derivatives with respect to G, let's say Q dot mu nu rho, or sigma, let's do sigma. And then Q, no, not Q dot, just like this. But these are all going to be 0, mind you, because our G is actually constant valued, the entries. It's okay, let me just finish though. Like this would be like that. Like that. It's just a gradient. And then 2 times the derivative of one and no derivative on the other one. Okay. But then Q double dot is equal to 0 because of this part, right? So Q double dot is either Z double dot or theta double dot, they're both constants, so this is equal to 0, i.e. energy is constant, so everything is conserved. It's pretty nice. Exactly what you would expect from a geodesic. Now, I would love to do the case for a ball, but it actually can't be done analytically from what I know, or at least I'm not able to do it. I tried many times. So I think next time I want to try to calculate the curvature tensor of the cylinder, stuff like that. That could be fun. Okay, see you guys. Thanks.